Hello everyone, my name is Arthur Zahn and I will give you a brief overview of our publication in which we use Memetic genetic algorithms to find piecewise linear approximations for time series. A time series is essentially a sequence of data points measured over time. For better visibility, it is common to connect those points. To store time series data efficiently and to prepare it for further processing, it is often necessary to compress it, and the compression method considered in our work is called piecewise linear approximation and works by having multiple connected linear segments which approximate the original time series. The segments are here displayed with the red dashed line, and the red points which define the segments are called the points of the compressed time series. For a given number of segments, our optimization goal is the mean squared error, which is based on the vertical distance between the points of the original time series and the respective values of the compressed time series. Some algorithms in the literature are restricted to only use existing points to define their linear segments, so for them it might look like this. While this restriction does not apply to our algorithm, we will refer to this restriction as sampling. We propose a genetic algorithm, or GA for short. A GA tries to solve an optimization problem by maintaining a collection of solutions called the population and evolving this population throughout multiple iterations. At the beginning of each iteration, new solutions are derived from existing ones and then modified slightly with random operators. Afterwards, the algorithm selects some of the new and old solutions to survive to form the population of the next generation. Genetic algorithms are very general purpose frameworks and need very little information about the problem they are actually solving. All they need to know is an encoding for the solution and a fitness function which they use to evaluate the individual solutions. To further improve the performance of such a general framework, we add problem-specific operators. First, we use a trick called seeding, in which we use existing compression algorithms from literature to generate solutions for the problem and feed those solutions into the initial population of our genetic algorithm. This accelerates the search, especially at the beginning. Furthermore, we propose a new local search operator which receives time series and which receives a compressed time series and is greatly optimizing it to get an even better solution. This is especially helpful to get the little details right, which can otherwise be very tedious if only relying on random operations. In our publication, we evaluate the algorithm empirically by running it on real-world and synthetic datasets. We compare it against other evolutionary approaches from the literature and show that we outperform them significantly in terms of speed and quality. Note, however, that those approaches from the literature are restricted to sampling by their representation, which makes the evolutionary research much more tedious and difficult. The other algorithm we compare against is Bellman's algorithm, which is also restricted to sampling, but actually computes the optimum solution for this setting. This makes it a great quality benchmark. What we find is that when given a comparable time budget as Bellman's algorithm, our genetic search manages to find solutions of similar or better quality than Bellman, though the improvement itself depends strongly on the dataset. Our other big result is that our genetic algorithm scales better with the input size than Bellman's algorithm. This graph shows the result for one of our datasets, and what we measured is the time our algorithm needs to find a solution of Bellman's quality and the run time of Bellman's algorithm. And what we can see in this case is that for input time series of 100,000 points, we reach a speed up of roughly 17. Though again here, the speed up reached varied by dataset, and overall for time series of 100,000 points length, our results varied between 7 and more than 100 as a speed up. Overall, our algorithm is especially suitable for larger datasets where it consistently manages to outperform Bellman and find good solutions. After this high-level overview, let us take a closer look at the most important parts of our genetic algorithm. We represent each solution as a bit array, where 1 signifies that there will be a point in the compressed time series. To enforce valid solutions, we make sure that there's a consistent number of 1s in each bit array, and that the first and last bit are always set to 1. So how do we get the values of the points? One way many algorithms from literature handle this is they simply assign the value of the original time series to their points. But what we actually do is we use regression to compute those values for the given times optimally. On the one hand, this greatly improves our quality in general, and on the other hand, it also smooths the search space and makes the genetic search much easier, as the algorithm can now focus on the overall structure of a time series instead of having to worry about the local values of specific points. Let us now take a look at the seeding operator. We use 3 different algorithms from the literature, each of which pursues a unique greedy strategy to compress time series. By using multiple algorithms, we hope to cover different input types and to achieve more robustness in general. Introducing those solutions into the initial population greatly accelerates the search, especially at the beginning during the exploration phase, and allows the algorithm to build on top of them. At the same time, we need to be aware that seeding introduces a bias into the genetic search, which can potentially lead the algorithm to bad local optimums. So this is something to keep in mind when using seeding. Another nice property, however, is that it is very extensible. So if you have a specific compression algorithm for your specific data type, or think there are other nice heuristics, you can simply insert them into the seeding operator and feed this information to the genetic algorithm. Next, let's look at the local search. The operator we propose works in a very greedy and simple manner. It iterates over the points of the compressed time series and optimizes each one of them locally. So it will start with this point here and place it between both of its neighbors in such a way that this part of the original time series is approximated as well as possible. So it will take this point now and place it down there, and then move on to the next point, this one, and place it a little bit to the left. Then it moves to the next one, and so on and so forth. And of course, after the algorithm is done, and after each right neighbor has been moved, the points are not locally optimal anymore, but it still greatly improves the quality of the compressed time series and is really important for the quality of our genetic algorithm. It is especially useful because the little details it finds and these local improvements are otherwise very tedious to find when only relying on random operators. Of course, just adding operators to our genetic algorithm does not necessarily improve its performance. For seeding, we already mentioned the potentially negative effect of the bias, and the local search is very computationally expensive. Consequently, we also verified the positive impact of the operators through empirical experiments. Here you can see the result for one of our datasets, and what we can see here is the mean squared error of the best solution found at a given iteration. So it essentially shows the development of a quality over time. The blue line represents the bare bones genetic algorithm, without seeding and without the local search. As you can see, it clearly performs worst out of the 4 approaches. The yellow line represents the algorithm using seeding, but not the local search. Since it's using seeding, it's starting with a relatively good quality, then takes some time to find a better solution, and then improves slowly. The green line, on the other hand, does not use seeding, which is why it starts at such a high point, but uses the local search, which allows it to improve rapidly, quickly overtaking the yellow line. Finally, the red line signifies the algorithm using both seeding and local search, and as you can see, it outperforms the other 4 approaches. And even when taking into account the computational cost of the local search, the added operators are clearly worth it. Finally, let's move on to our results. The evolutionary approaches we compare against have been proposed by Duran Rosal et al., who generously shared their code with us, which allowed us to do these experiments in the first place. In particular, we compare against their particle swarm optimization algorithm and their coral reef optimization algorithm. What you can see in those 3 columns here is the mean squared error of the result after running all 3 algorithms with a comparable time budget. For convenience, we have scaled these errors, so the number here is not actually 410, but 410 times 10 to the power of minus 5. As you can see, we consistently manage to outperform them significantly in terms of quality across all the datasets. Again, please keep in mind that the other algorithms are restricted to sampling, which makes evolutionary search much more difficult. Another interesting result you can't see on this chart is that on many of the datasets, the solution found during the first iteration of our algorithms was actually better than the final solution of the competing approaches, though this win can be most certainly accredited to the seeding operator. Our main comparison is against the deterministic Bellman algorithm, which computes the optimum solution under the sampling restriction, and is thus a great quality benchmark. As on the previous slide, we analyzed the quality reached by our algorithm when given a similar runtime budget as Bellman's algorithm. What you can see in this column here is the ratio between the mean squared errors between the solution found by our algorithm and the solution produced by Bellman. The low ratio is desirable, as it means that we outperform Bellman, whereas the ratio of 1 indicates that both algorithms produced solutions of exactly the same quality. We find that there are some datasets on which we significantly outperform Bellman in terms of quality, while there are also datasets where the solutions produced have a very similar level of quality. One contributor to this variance based on dataset is probably that the difference between the optimum solution and the optimum under sampling also varies depending on the dataset. So there might be some time series on which the solution produced by Bellman is actually very close to the general optimum. Another interesting result, which also plays into this difference, is the scaling behavior of our algorithm when running it on time series of different length. Here's the result for one of our datasets, where we measured the time our algorithm needs to find a solution of Bellman's quality, which is indicated by the yellow line, and we also ran Bellman's algorithm and just measured its runtime, which is indicated by the blue line here. We did so for input time series of different length, ranging from 10,000 points up to 100,000 points, and the numbers next to the blue dots indicate the speed up reached. So on this dataset, for an input size of 100,000 points, we reached the speed up factor of roughly 17. Across all datasets, we consistently scale better than Bellman, though the final speed up reached again differs based on the dataset. So on the result on another dataset here is only a speed up of 7.5. And we can see here that at the beginning for 10,000 points we were even slower than Bellman, whereas there are also time series which are very friendly towards our algorithm, where we then managed to reach a speed up of above 100. From this we can conclude that our algorithm is especially suitable if you have a large data set and really want to minimize mean squared error. Another practical advantage of the genetic algorithm proposed is that it can be stopped at any time, and you will still receive a good result for your time invested. So those are our main results, and if you want to know more details, we encourage you to take a look at our publication. Or if you have any questions, please feel free to reach out to us directly. Thank you for your attention.